My name is Ashot. Thanks for hosting me. I'll be talking about programming for GPUs. And hopefully there's a link down here. That's my GitHub repository. I strongly encourage everybody to look into the repository, and there is the copy of this presentation of the talk and the code, so it will be easier for you to track. We have a lot of content to cover today, so without further ado, I'll jump right into it. So I'm actually 24 years old. I'm from this city. This is my home base. I've been doing software development for most of my life, and the first time I used graphics API in my product was about 10 years ago. In the past, I worked on everything from web, mobile, desktop, then a couple of years in scientific computing, and for the last 4 years, I've been working independently on my own high-performance computing framework targeted primarily at artificial intelligence workloads. And obviously, this implies a lot of programming for GPUs, so I'll share some of my knowledge that I've gained in the last 4 years. And here's who this talk is primarily targeted for. So obviously, we're all familiar with C and C++. I expect you to know what a GPU is and what's the difference, the basic difference between a CPU and GPU, the number of threads maybe, the hierarchy of the memory. And then generally, this talk is more targeted towards people who do number crunching. So if you are in AI, if you do image or video processing, or let's say you run physics simulations, you prepare games, then you probably should be familiar with some of the things that I'm talking about. And you may use some of the insights. So why GPUs? So many of us have seen charts like this. This is some kind of a speed up for random algorithms comparing the performance on the CPU to the GPU performance. And very often they claim outrageous numbers like 35x improvement. And it sounds amazing, but I'm not really sure that it's all that easy and shiny. So our hope for today is the following. I guess everybody has this hope, no matter if it's today or not. We want to write our software just once. We want to run it everywhere, on every kind of device. We want to achieve maximum performance with a minimum boilerplate code. So we want our code to be very saturated. It generally implies having just one CPP source file with everything we need for the CPU, for GPU, and all kinds of accelerators. We want to run it on Intel CPUs and their integrated GPUs, on all kinds of NVIDIA and AMD products, as well as FPGAs, potentially. For all of that, we need a ton of stuff. We need a unified language. We need modular compilers. We need to have tools that allow us to tune our software, and we need clean APIs. So the problem is extremely broad, and I do not expect one solution to cover all the bases for every single one of you. So our goal for today is to prepare 4 different recipes, 4 different scenarios, 4 different combinations of tools, so that you can go home and pick a set of tools that best suits your purposes. To put it in a more formal way, we'll start with the very introductory material. We'll slowly go into the practice mode, and then we'll end up talking about more senior architecture, software architecture-related stuff, how to combine all of it, how to use the theory and practice we gain to build your future products. So for you to interface with the GPU, you need to communicate with it over a standardized API. And the oldest one of those is OpenCL. It was actually proposed back in 1992 by a company called Silicon Graphics. And the company is already dead. It's actually dead since 2009. But the API, the OpenCL, is still alive, and it's still the dominant force in the graphics industry. They have support for almost every kind of device, though Apple, they should not sound strange. They basically deprecated support for OpenCL a year ago with iOS 12. Then came CUDA in 2007 with NVIDIA as base platform. It's very platform specific, but the cool thing about CUDA is that's basically the first standards that's specific for compute. OpenCL was a graphics API, while CUDA is more compute targeted. OpenCL came close. In 2009, it was unveiled and submitted by Apple into the Kernels group. It's supported on almost all kinds of devices, and on this chart, you can see the amazing adoption rate. It's kind of outdated. It's for 2015. But even back then, almost every kind of platform had support for OpenCL. Maybe it's version 1.2, but it's still support. So even though OpenCL was proposed by Apple, they didn't continue working on it for too long. Currently, Xilinx is the company that maintains OpenCL within the Kernels group, and they basically build FPGAs, which implies that OpenCL, out of all standards that I'm going to talk today about, has the best support on FPGAs. Metal is the new standard unveiled by Apple for their devices internally. OpenCL is based on C. CUDA is based on C++. Metal is based on C++. But Metal is only for Apple devices. OpenCL is very generic. It's running everywhere. And now the youngest standard of all, Vulkan, probably the most complicated standard of all. It was proposed in 2016 by AMD. It's currently in the Kernels group as well. It runs everywhere. It's extremely powerful. It runs even on Apple devices. I'm not just saying MacBooks. It's also iOS. It also runs on Android. It runs everywhere. But it's really hard to start using it. So for us to start comparing it, we can take a few key features and build a few charts, but it's too much. Let's clean the clutter and focus on our main priorities today. So CUDA and OpenCL are the two main rivals in the GPGPU space. Vulkan is the new contestant. Vulkan is somewhat more generic in a way that it doesn't require you to write your code in a specific language. Vulkan takes special intermediate representations called SPIR-V format. And this intermediate representation is very generic, though Vulkan as an API for the host code for the CPU is extremely complex. So a benchmark, well, not a benchmark, the Hello World application in graphics is generally drawing a triangle on a screen. And drawing a triangle on a screen with Vulkan can take 1,200 lines of code. So it's not really a Hello World scenario. We'll talk primarily about CUDA and OpenCL. And as they are solving more or less the same problem, they are very similar on the language level. They have more or less the same abstractions. The language that you would want to use for parallel programming should probably have two of those things, synchronization primitives and the memory qualifiers. So synchronization primitive is something that lets every single thread on a device to understand its specific role. So while the kernel is running, every thread can query its own position and its own purpose within the entire operation. And then memory qualifiers is something that's more for a compiler. So it basically limits the visibility of a specific memory region. So you can mark every part of memory as either a global memory or a shared memory. And there's some specific distinctions between those. So a global memory is the simplest concept of all. It's like the heap. It's everything. It's a piece of memory that every thread on a GPU can read and write from. And also the CPU can read and write from this part of memory. It's generally the largest chunk. Then, as you have thousands of cores on your device, it's logical to group them into small clusters, into groups of threads, let's call them this way. And on CUDA, the memory block that's shared between a group of threads is called a shared memory block, while in OpenCL it's called local. Here's the place where confusion starts. So as you can see, local is also the name for the type of memory that's limited for a specific thread in single-threaded memory pool. So one thing to note here is that the same thing that is called local in OpenCL is not the same thing in CUDA. So it's an important piece of distinction. And the last fourth tier of memory, it's generally some kind of constant memory, something that only CPU can overwrite. But all the threads on GPU can only have read access to this part of memory. And just for the sake of comparison, even though we're not talking explicitly about OpenGL, OpenGL being a graphics API, even though it's designed for the same kind of devices as OpenCL or CUDA, it has different abstractions. So unlike compute APIs that have global, local, private, and constant memory pools, this one has various buffers, vertex buffers, textures, etc. Not important for us today. What's important is to understand that the abstraction in the language is not the same as the hardware specs. So we have three totally different devices, an Intel CPU, a Titan V GPU by NVIDIA, and a GPU by AMD. They all have different specs. So compute units is basically a hardware spec. Syncable groups, it's a software feature. So syncable groups, it's something that OpenCL knows. And the understanding of a device from the OpenCL perspective is totally different from the way the hardware is organized. The same way with memory. We have constant buffers and the local memory on the device, which is somewhat similar in its basic principles to level 1 and level 2 cache on our devices. Though at level 1 cache on this specific GPU on the right is 1 megabyte, while the constant buffer is just 64 kilobytes. To make things even more confusing, as much as I understand, NVIDIA generally has just one real physical constant buffer on a device, and it's generally around 64 to 128 kilobytes, while AMD GPUs have multiple constant buffers. Each of them is 64 kilobytes, but once you exceed this buffer, you start allocating in a global memory. That's why a language abstracts away a lot. And on the language side, they're extremely similar. So there is basically a one-to-one mapping between almost every keyword in OpenCL and every keyword in CUDA. The memory types that I've described before, they need some keywords in the language. Here they are. And for people who've never seen a GPU code before, in the bottom left corner, this is a function declaration in C for a CPU that basically sums up two vectors, xa and xb. It takes also a pointer to the output, which is y, and xlen would be the length of all those arrays, which we want to sum element-wise. The same function declaration, but in OpenCL for the GPU code, will look like this. It's on the bottom right. For every single argument, we need to specify if it's a global or a shared variable or something else. To continue, here is the mapping between terminology surrounding CUDA and OpenCL. And there is also one-to-one mapping in terms of kernel indexing. So every thread can call any of those methods, which are basically part of the language, to understand their role within the specific computation. This will get clearer quite soon. The only piece of, the only difference basically arises when you start considering different synchronization patterns. So a synchronization pattern is something that kicks in when you write a non-data parallel program, but instead a concurrent program, something that should work with a large amount of data, but it may work on it simultaneously using multiple threads. So like every single thread can be simultaneously using the same piece of data. To synchronize threads, CUDA has a special keyword or a method called thread fence, which is basically a method that applies to all the threads on a device. There is no analog in OpenCL world. So there is no way in OpenCL to make every single thread on device stop, wait for the others to reach the same point in the program, and then continue from this specific synchronization point. In OpenCL, as in some other APIs, the only set of threads that you can synchronize with each other is only the threads within the same group of threads. So you predefine the set of threads, and then you can synchronize them with each other. There are also a couple of other synchronization patterns in OpenCL, read mem fence and write mem fence. And I've worked with a lot of AI and GPU libraries, and I haven't seen once anybody using this, so I cannot really tell anything useful. Actually, like the only synchronization protocol over here that influences primarily the computation and not the memory is the top line. This is the one that's used the most. The second and the third line are also quite rare. So as we've seen, parallelism in the language in OpenCL and CUDA is reflected more or less the same way. So let's dig into code and see how it looks. If we have a data parallel task, it means that we have, let's say, n elements in our array, and we want to map every single element to some kind of output. Let's say apply a sign function to every single value in the original array and get the final array. A probably even simpler problem is just summing up to vectors, an operation that everybody knows from linear algebra or from programming, whatever suits you. To implement this in C, we can write something like this, a trivial code with the same signature as before, summing up two numbers. Just an explicit for loop, a very serial, very primitive code, hello world basically in the compute world. This is the same version for OpenCL. As you see, I'll jump back for a second. We have an explicit for loop over here, but we don't have an explicit for loop in the OpenCL kernel. That's because this is just the GPU counterpart. There is also a code that runs on the CPU that basically controls the number of basically thread allocation or work allocations. And every single thread just internally queries its own purpose, which is in this case described by index I to understand which numbers it is to sum up. Let's get a little bit more unique, and basically this is the only case when somebody's showing GLSL in the high-performance compute world. So if you, for whatever reason, cannot write OpenCL or CUDA, you will probably write a GPU shader like this. It has the same purpose. But for today, let's first consider concurrent problems. And the easiest one of all is array reduction, summing up all numbers in an array to their sum value. The C code is as obvious as the previous examples. We just take an array, we explicitly loop over it, we sum up all the numbers to the output variable, which is y in this case. And y in this case is not an array. We could have easily passed it by reference the same way if it was like pure C++ declaration. In the GPU world, we cannot make all threads write into the same variable for obvious reasons. We've all written parallel programs. We don't want data races. We don't want undefined behavior. That's why we generally split the original problem into multiple iterations. Every thread receives a subset of original problem. It runs internally in some kind of serial fashion, but as all threads are working independently, we get the result much faster. And here's how it looks in OpenCL. Very simple. So this code, believe it or not, does the same array reduction. It just sums up the numbers in the original array. And the function name is reduce simple. This is not the only version of reduce that I've written. There are actually six versions of this same function in the GitHub repository that I've just mentioned in the beginning of the talk, doing exactly the same, and they have huge performance differences. So actually, there is one order of magnitude performance difference. So if one of them runs in 10 seconds, the other one can run in 100 seconds. And there is no explicit, easy way to understand if this solution, the second one, is much better than this one. Well, in this specific case, there might be some hints. For example, the loop unrolling over here and the way the memory barriers are organized. But the purpose of this slide is just to make you believe that writing concurrent kernels, non-data parallel kernels for GPUs is extremely complex. So we want higher level tools. Here where linear algebra libraries kicked in. This is basically the lowest level of abstraction that we generally discuss after the OpenCL and CUDA as a language. So they're the two most popular linear algebra packages, which are BLAS and LAPACK, and they're basically as old as my parents. So BLAS was originally suggested in 1973, and they were originally designed and implemented in Fortran. They have various implementations. They're generally platform specific, but you can easily jump from one to another as the API is basically the same. Intel MKL is a very broad library for Intel hardware. CUDA is obviously for NVIDIA devices, and CL Blast is an open source implementation for OpenCL. They do more or less the same stuff. BLAS is a more low-level thing than LAPACK. So BLAS has more arithmetics kind of stuff, like multiplying matrices or a dot product of two vectors, while LAPACK more focuses on the actual linear algebra, things such as eigenvector problems and eigenvalue analysis, and then matrix factorization. But what if you want something very simple, like the same problems we've just discussed, reducing the array into a sum of numbers, and then maybe summing up two arrays of numbers? Basically, BLAS has 152 function definitions in it. It has functions for single precision arithmetics, it has functions for double precision, for complex single precision, and for double complex numbers. So, pretty complicated, right? Though unfortunately, there is no easy way to sum up numbers using BLAS or LAPACK, and there is no easy way to sum two vectors. Instead, it provides some very complicated functions, which I will not jump into it. But another problem that I will mention over here is that even though every single kernel separately and every single function implementation in those packages is generally very well optimized for specific hardware, is that taking those fast kernels and chaining them together will not result in fast pipelines. And the problem here is data locality. We'll talk about this in a minute. We'll just get back to the chart I had in the very beginning of the talk. This was actually a chart that I took from NVIDIA website. It was published along with the QBlast version 9.2, which compared performance of GPU in the BLAST operations to the Intel MKL, as much as I remember. And what they did, they've compared a Titan V GPU, not a Titan V, but V100 GPU, with a Xeon E5-2690 V4 model of an Intel CPU. It's not a very fair comparison, because the GPU is 1 year younger. It was presented in 2017, and it cost 4 times more than the CPU. So the GPU was $8,000 worth, and the CPU was $2,000 worth. And the notable thing here is that as we progress, the differences between GPUs and CPUs kind of shrink. So CPUs nowadays are getting much more floating point performance than they had before. That's why the difference between, let's say, a modern-day CPU like Intel Gold Edition 6262 will be much smaller between like a comparable GPU, with a comparable price GPU, let's say. Another level of abstraction after linear algebra libraries is libraries like Eigen, ArrayFire, etc. And as you can see, they're kind of ordered in the descending order of their popularity. So Eigen has 10,000 stars on GitHub, and ArrayFire has almost 3,000. Please, guys, raise hands if anybody had worked with Eigen. More hands. Okay, I guess there would be even more than that. But unfortunately not. So Eigen is a great library for linear.
I'm sorry to interrupt you. We have some issues with the translation, so if you can just stop for maybe a couple of minutes on maybe this slide or somehow, so that we figure out. Okay.
Inform me once you're ready. Like if somebody has a question in an audience, I can answer right now.
Yeah, you can just maybe answer some local questions while we're
like if somebody has a question right now. Oh, I'm good at explaining. Perfect. If you want, I can jump back to the previous slide and talk more about them. Let's say somewhere here. So one of the problems that I didn't have time to talk, I guess I didn't have time to talk about, is that, for example, if you want to perform an array reduction, so if you want to add up all numbers into arrays pairwise, using BLAST and LabVac libraries, what you will end up doing is basically dot products with unit vectors, just expecting to result with the same value. And if you want to sum up 2 arrays of numbers, you will basically end up with a function that is called saxpy, whatever it means. So as you see, the names of function s dot and saxpy look very much like Fortran function declarations. Another interesting query will be like to see if anybody had done programming in Fortran before. Can you please raise hands if you've done Fortran programming? Less than with Eigen, but it's more or less comparable. Yeah, I share your pain. Yeah, I've done a few years of Fortran programming as well. Are we ready to go?
We'll be back just in a minute because the Munich actually can hear you but can't see the presentation. So we'll just restart the presenter mode on your laptop, and hopefully after that you can proceed successfully.
Yeah, sure. Okay. Are we live? Perfect. Is Munich here? Can I go on?
They confirmed.
Okay,
cool.
Perfect. So here's where we stopped. So the popularity of the libraries, and then some people used Eigen before. Did anybody use any other libraries other than Eigen? Just one guy? Like 3, 4? Okay. So they kind of solve more or less the same problem. I call them lazy evaluation systems because generally they act in somewhat different ways. For example, Eigen is a templates library, so after you apply some kind of function to a matrix or an array, you end up with a very complicated template that basically encapsulates the type of the operation that you want to apply and the original input, so it's kind of a graph. And then ArrayFire is somewhat different because it's not type safe. It's very polymorphic in its nature, and after you compose multiple function calls together, behind the scenes what it does is basically runs just-in-time compilation to produce a dependency graph of operations that you want to apply to the same input. So Eigen is not strictly speaking a GPGPU solution. They were originally designed for CPU execution. They were accelerated with OpenMP, a very common standard. They have experimental support for CUDA, and some people are trying to port it to OpenCL, though the progress is very minimal. Arrayfire is an actual GPGPU solution. It's not type safe, not in a C++ fashion, and but unlike Eigen, it has tons of backends. So if you open the Arrayfire website right now, you can actually download binaries and precompiled libraries for all kinds of backends that you may have, for all kinds of platforms, including Windows, macOS, etc., or like Linux, and run your accelerated code using those libraries. The problem with using those systems in general is that they are very different from each other. So LAPACK and BLAS are industry standards. They have very strict defined signatures for every single function call. So if you write your software around a BLAS library, if you want to switch to a different vendor within, let's say, a couple of months or a few years, the chances are you will easily be able to port your original code to the final target. In the case of those libraries, it's much more complicated because they have very different classes, they have different function calls, and you will need to rewrite some of the logic. Let's get back to the data parallel programs again, but with the high-level tools. So how can we make them even faster than they are, like, even now? So the one thing that we haven't tried optimizing yet is the data locality. So actually, from the physics perspective, performing a floating point operation, let's say summing up two numbers, is a very cheap operation. It basically requires 1 picojoule of energy, though those numbers are generally true for 28 nanometer fabrication process, and currently it's even smaller than that. While sending that specific floating point number, or let's say a 32-bit integer, to the DRAM, or like taking it back, requires 1,000 times more energy. So obviously, this is the thing that we need to optimize. We should fuse multiple operations together so that once the data gets from the DRAM into the registers of our GPU, we apply as many operations one after another without sending the data back to the DRAM. We've done this thing for million times in high-performance computing for CPU. In the case of GPU, it's a little bit different, but now we have better tools. And one of the tools or one of the language features that we may introduce to get better at fusing kernels is actually order descriptors, as I've named them here, though it's not a very good term. Maybe you can find a better one later. So imagine a function like this. I'll be now talking about a system called Halide. This one looks like a very symbolic representation of a function. It's very declarative. We basically define a function that depends on I. It takes two arrays and sums up values in these arrays. But then there is some boilerplate around it. This is our original function responsible for summing up two arrays, implemented using special library / embedded language / compiler toolchain, which is called Halide. Halide was designed in 2013 in MIT, specifically for image processing purposes. And the beauty of it is that it makes loops implicit. So as you can see, function body, the actual operation, is separate from the for loop. We have some boilerplate in the very beginning, which defines the buffers in the way that Halide can comprehend them. But then after we've defined the buffers, we just define the function body just once. And everything rest is tunable and modifiable. So a function call realize will basically compile the function above using just-in-time compilation, and will immediately run the result kernel with an argument xlang. So basically, it produces a kernel, and it immediately parallelizes it over the entire length of the array. Wait for it. I've just modified it. I've just made it parallel. So this one wasn't parallel. This was just code. Just by adding parallel over here, just one single statement, I've transformed the original function into a data parallel function. Though things and magic doesn't stop here. I can easily vectorize the same function without changing it. So I've just changed one single function call, And what this does, it basically transforms our original for loop into strided vectorized set of operations that we apply. So instead of basically computing sums of floating point numbers, we compute sums of vectors of length 8, which is somewhat equivalent to SIMD operations that we have in the CPU, single instruction, multiple data. But the beauty of Halide is not even in that. It's actually in the variable splitting. So previously, we had just one variable I, over which we iterated in our original data set. We can transform our one-dimensional for loop into a nested two-dimensional for loop. So basically, we can transform a for loop over I into two nested for loops, one over j and one over k. So if we have, let's say, 1,000 data points, we can either run it for every I from 0 to 1,000, or we can run it for every j from 0 to 100. And within the for loop for j's, we can also run it for every k from 0 to 10. So we end up with the same 1,000 operations, just split into two levels of nested for loops. And we can easily parallelize over the first variables and then do loop unrolling over the second one. This is the trick we often use in high-performance programming. And let's get to some more advanced examples, because the ones with summing up to arrays of numbers are just too trivial to show you the beauty of Halide. We have an image blurring operation. So we take an image and we find average values for pixels first horizontally and then vertically. So we basically run over the same data set twice. The first run is actually very slow. The second one is fast. On some devices, you can get 15x performance difference in terms of their speed, just because one of them explores data locality and the other doesn't. But this is just a simple reference implementation. So if you want to build a high-performance solution, this is what you end up in C++. You will generally use platform-specific SIMD instructions. You will spend a ton of time trying to arrange them in the right way. In Halide, you achieve the same performance on same devices with much cleaner code, though it's not very C++ looking. But on the opposite side, it takes much less time to design. How much less time? Well, that was actually even more sophisticated example. So the image filter that I've shown was blurring filter. There is a Laplacian filter, which is sometimes used in, let's say, computer graphics and computer vision problems. The reference implementation for Laplacian filter is about 300 lines of code. Adobe, a company responsible for image editing software like Photoshop, wanted to build their faster solution for their devices. They've hired an engineer who spent 3 months working on the implementation. He ended up with a 10 times faster solution, which was 1,500 lines of code in terms of length. Then another guy spent basically 1 day practicing with Halide. He wasn't even a senior developer, he was just a junior. He wrote 60 lines of code as opposed to 1,500. He spent just 1 day, and he doubled the performance numbers from Adobe implementation, from those complicated 1,500 lines of C++ code. And here's the best part, just wait for it. The same code runs on GPU. So the C++ implementation was SIMD specific, so C++ specific, so CPU specific. This one is generic. You write it once, it runs 2 times faster than the optimized version on the CPU, and it's 7 times faster on the GPU. I guess it's a win-win. But this is not the only solution that I'm going to tell you about. Here is SyCL. SyCL is like the next step of evolution in the future of OpenCL. It's basically the first step for us to get to a heterogeneous computing stage. In the very beginning, I told you that we want all our code written just once. And ideally, that implies that we have just one CPP file. If you write CUDA code, you have your CPU code in a CPP file and then the CUDA kernel separately. The same for OpenCL, but not for SyCL. SyCL is basically a next-generation system that allows you to write functions in a more C++ way, though with some boilerplate. The problem with SyCL is that it's just a library, in a way. So they do not change the original language. They cannot enforce new keywords into C++ committee. But what they require is compiler support. So to run this code, you actually need a compiler that understands which part of this huge lambda expression should actually be vectorized and parallelized on the GPU. And you see this one lonely line over here? It's like the only part that is meaningful. The rest is just boilerplate that specifies the buffers and the access patterns, if we are allowed to read or write into this buffer or not. Here's what we want. And we are probably getting it, just not today. So after we get C++20, after we get ranges TS, after we get parallelism TS, we'll be able to write STL algorithm expressions, just we do today, by providing the first variable as a policy. So SyCL is also trying to introduce its own policy. And the expectation is that this code will be fully identical to this one over here, though much more beautiful. Here's how it looks. Self-explanatory, right? I hope not, because it definitely doesn't feel self-explanatory to me. Here's what you need to know. So you get one single source file, which is a C++ file, and then the compiler, who already knows how to work with this kind of data, with this kind of source file, splits this into two files. And the left branch is kind of standard. We're all familiar with this, just a standard GCC, LLVM, Clang, toolchain, etc. The right part is what interests us today. The data in the source code should first pass through a SyCL device compiler, and then afterwards it generates a device code which is formatted into a special SPIRV binary format. SPIRV is very different from other formats that we are familiar with, either executables that run on GPUs. It's an intermediate representation, so it's very generic. So QBin file is the extension of executables that you run generally on NVIDIA GPUs with CUDA. But the problem with QBin is that it's architecture dependent. So if you have a Volta GPU in your server and the Pascal GPU in your server, both made by NVIDIA but two different generations, you will need two different QBin files. But NVIDIA has PTX format as well, which is an intermediate representation format. Though PTX is only limited to NVIDIA. What's with OpenCL? With OpenCL, if anybody of you have tried writing large programs in OpenCL, you end up with the same problem. So you generally want to split large programs into multiple source files so that the logic is, let's say, separate from data management, separate from number crunching. But once you compile it, you need to link all those files together. And linking files in OpenCL is not always trivial, and some implementations of OpenCL have bugs. Namely, NVIDIA had a bug some time ago. I'm not sure if they have now or not, but it's extremely hard to link together multiple OpenCL files into the same binary once you want to compile it. So generally what people do is a dirty hack. They just write a function in C++ on the host side that takes multiple files in the same directory that are related to the same project, all with the OpenCL extension. It reads them from the disk and concatenates the strings together as if it is just the same source, like one large source file. So it's a mess. SPIRV, being the next generation thing, is expected to not have all those stupid problems. And even though it's that powerful, it basically builds around the existing LLVM infrastructure. So the only new part on this entire chart basically is this, SyCL for ISO C++ front end, the upper right corner. All the rest already exists. It's a huge, tremendous project that spits out the same SPIRV binaries, no matter what kind of high-level language input you give to it. But to be honest, for me, it's a bit too complicated to dig in and to learn all of the aspects of it, because it's huge. It's like, I've checked today, I've cloned the LLVM Clang version, and it's 95,000 files. Source files, and out of them, like 35,000 are C++ source files, and out of them, like there is like 5.5 million lines of code. That's excluding comment lines and empty lines. What we get? I've told you about Halide. I've told you about SyCL. This is the Kernel Fusion benchmark results for those two systems. So on the left side, we have OpenCV, a system that we didn't talk about today. In the middle, those are the numbers for Halide. And on the right side, it's SyCL. So what we see here is that in the beginning, we had 3 separate GPU programs. The first took in an image, transformed it from the RGB format into HSV format. The second one applied some kind of transformation to an image, and the third one transformed it back to RGB from HSV. So using and exploiting data locality, we can actually merge those operations together as if it's like one super function. So we remove this unnecessary waiting time for the GPU and improve our performance 3 times. But it doesn't work that way for really complicated scenarios. So like editing a picture, an image like this is a very data parallel problem. If it's a little more concurrent and less data parallel, you will not get results as good as this. So it's all about compromises. Let's get to the 4 recipes that I've promised you in the very beginning. And we'll start with a unified solution, something very hybrid in its nature. So maybe some of you want to run the same binary on all kinds of devices. Maybe you want the SPIRV format. In this case, you should probably use the OpenCL as your language, as your go-to language to describe your kernels, and then you should use the compiler open sourced by Google, CLSPV, that lets you transform OpenCL into SPIRV format. It's claimed that sometime in the future there will be interoperability between the current Vulkan pipelines and the OpenCL as a language, as a toolchain, but so far we don't need it. That's why this compiler by Google really kicks into place like a very neat, nice thing. And I would also suggest wrapping it up once you have all the binaries in SPIRV. When you write your host code in Vulkan, do it in Vulkan. Here's why. If you just write OpenCL code and run OpenCL using OpenCL API on the host, you get all the weaknesses of old school APIs just because OpenCL is like 11 years old, at least 11 years old, because it was developed before that in Apple. Vulkan has a much more concurrent design. It doesn't have singletons, so there is no single variable managing the entire state. It's very flexible, and one of the most interesting aspects and features that it has in terms of its flexibility is the logical device concept. So when you have a physical device, a GPU in your server, it's just a physical device, but a Vulkan needs to interface with it somehow, so it generates an instance called logical device. But if you have multiple GPUs connected with each other within SLI bridge, you can fool Vulkan into thinking that this entire set of GPUs is actually one single GPU. So you can run your single program designed for a single GPU setup on multiple GPUs, while the program itself thinks that it's running on the single GPUs, but you get double the performance, I guess. It doesn't work very well all the time, but it's a feature one can use. And a cool aspect if you do games or UI applications is that Vulkan is a compute-capable API, but it's graphics-first API. So you will be able to control the same workflow. You will have the same workflow and the same wrapper classes for Vulkan for both your graphics applications and for your compute applications. Though there are some downsides, the major one is that you have separate code bases. You have separate files for OpenCL kernels, and you have separate C++ code. And the compiler by Google is at experimental stage. But to make things worse, there is no support for some of the very interesting CUDA features, which are important if you get to a specific point in high-performance computing. I can answer the questions related to that after the main part. So the second solution is a flexible solution. It's basically all about Halide. Halide is a very self-contained system. It has everything you may need. So it has an embedded domain-specific language, which is basically a library in C++. It has its own compiler toolchain that is like not very large. It's built all around LLVM. It's capable of emitting the same binaries for every single platform you may think. So with OpenCL and SPIRV, what you end up with is one single binary, an intermediate representation that runs on NVIDIA GPUs, on Intel CPUs, and it's the same single file. With Halide, the approach is different. After you've defined the shape of your computation in Halide, you are calling basically one single function in the same library, compile with different arguments. And depending on what kind of argument you provide, the function, you're basically sandbox environment outputs multiple executables for every platform that you've requested. So you'll have separate QBean files for your NVIDIA GPUs that you can further optimize somehow or debug. You will have separate files for your OpenCL stuff. But the downside of all of this is that Halide is Turing incomplete. Yeah, let's face it. It was designed as a graphics processing system, and it does not have any nice way for you to describe for loops within a specific thread of computation. And without for loops or while loops, there is no Turing completeness. There is no Turing completeness. Obviously, there is no support for recursion as well. There are some dirty hacks how to get around some specific problems, but in general, Halide is not Turing complete. And another problem is that it's an image processing system once again, so it has limited support for types. Let's say in AI community, we often work with half precision floating point numbers, and those specific rare types may not be supported on platforms like this. The last solution is the cleanest one. So if you like sleek, nice, modern C++, without, let's say, pointers or type erasure, you want just templates, then SyCL is the way to go. Though we've already discussed the problems of SyCL, and basically every single positive side that SyCL has basically comes with some kind of a negative aspect to it as well. The easiest one basically to grasp is that is the bottom line. So SyCL is built on top of the OpenCL infrastructure, and it helps you transform. It can help you to transform your code into like OpenCL compatible stuff. But the OpenCL interoperability comes through the boost compute. So it's not like direct interface to an API. You have like a separate library for it. And then the largest downside of all is that the implementation requires compiler support. So you cannot just run it randomly on any compiler that you like. You should wait until the compiler gets support for all the features that you need. And if you want the sleek version, like the SyCL algorithms that I've shown, then you may probably end up waiting for another 2 or 3 years. And then the simplest solution, like the most important part, probably. It's something that you can use like today, even if you have like very minimal knowledge of GPU. You can go home, download the library like ArrayFire, and start playing with it. It's a very simple way to start, but it comes with somewhat obvious downsides. I wasn't really very much explicit in terms of the downside you get, but like for obvious reasons, the performance will be suboptimal. It will be super easy to use. It will sometimes be cross-platform, sometimes it's platform-specific. And another thing to note here is that with, let's say, ArrayFire, you can run into some licensing issues. So there are CPU versions, not CPU, there are desktop versions, as much as I understand, as much as I remember, are totally free. But if you want to run this, the code written with ArrayFire on GPUs on, let's say, iOS or Android, you may have to negotiate a deal for that. And here's the table. So if you take just one thing from this entire talk, from this like entire hour of me presenting stuff here, it's this table. So a more or less complete understanding of what is the landscape today. If you are a little bit more enthusiastic, you can merge them together. So if you want maximum performance today, and you are ready to get dirty and like start tweaking and write your own software, then probably you should write OpenCL and SPIRV kernels for stuff that cannot be expressed in Halide, just because Halide is Turing incomplete. And then do the rest in Turing, in complete Halide. And then merge everything together using the Vulkan API on the host side. If you are looking into the future, then probably you should wait till SyCL. And the easy part about SyCL is that if you're fond of STL algorithms and your entire code base is currently filled with STL algorithms, transforming your original version into a GPU-accelerated version will be just a matter of one single regular expression. So every single IDE, and I'm pretty sure CLion as well, will let you run a regular expression transformation that will take your software will find every single call to SyCL algorithm and then just inject the SyCL policy as the first argument to that function. This is like hazardous and dangerous. This is more about the stuff that I like to do. Do not repeat it at home. If you are as enthusiastic about parallel computing and high-performance computing as I am, you may end up doing something much more complicated and maybe even interesting in a way. So we've discussed various aspects of languages like OpenCL and CUDA, which abstractions they introduce to make our code more expressive, something that C++, let's say, lacks right now in terms of like parallel computing. So we may think of some custom languages that will incorporate all the beauty of Halide and CUDA and OpenCL with the modern abstractions that we have in C++. We can try to work on our own libraries and our own compilers. And this is the topic that I can talk on for hours. And if you want, we can continue in during the break. But before we finish, there is one more thing that I want to show you. Some kind of approximation of the high-performance computing stack, or GPU stack, if you will. So I was spitting keywords and buzzwords all day long. GPUs, AI, symbolic computations, parallel computing. How do they all merge together? Well, this is a very approximate view of mine. We've actually discarded some of the topics over here. We've actually discussed the 4 of the 6 sections, the 4 of the 6 lines over here. The reason I'm saying it's approximate is because some of the technologies and some of the libraries and compilers simultaneously fall into multiple categories. But if sometime in the future you take the roadmap and the recipes that I've described and want to start exploring how much further you can push it and which other technologies you can build around them, maybe this chart will help you understand what already exists. So there are already, let's say, AI libraries that built on top of Eigen and ArrayFire. There are already compilers that take in CUDA code and OpenCL stuff and then emit binaries that are optimized for AI workloads. Let's say TVM is a good example of that. But in general, this is how the GPU landscape looks like. And this is how I want to end. Thank you, everybody, for coming and listening. And here's the GitHub repository with all the code. It has examples for Vulkan, for OpenCL, for OpenGL, for SyCL. I may add CUDA in the future. And it has raw, plain, old school C and C++ as well. So feel free to use. Thank you.
Can you guys hear us? Hello?
Yeah, cool.
Yeah.
We can hear you, Minik. Do you have questions?
You have questions?
Oh, perfect. So, if no questions at all, feel free to. Oh, there is one. Okay.
So you were talking about a lot of high-level APIs. One of the things which come to my mind is most of the, if you want to run CUDA, they are all tied to non-embedded platforms. So you need a proper SMP operating system in order to run them. If you want to use these kind of application in bare metal systems, what kind of options you have there?
In embedded systems, okay, let's get back to our beginning on the chart with the OpenCL adoption. So as I've shown you, there is a one-to-one mapping between almost every feature in CUDA and in OpenCL. So it's very easy to transform the source code that you run for CUDA into an OpenCL code. And then what I would do, I would actually let the compiler do most of the magic. So embedded devices actually have relatively good adoption rate for OpenCL. So instead of using CUDA as your primary language for general purpose computations on GPUs, I would rather use OpenCL and then just use the compiler and the OpenCL API provided by the vendor of your embedded device.
Cool.
Is that answering your question?
Yes, somewhat. But if you use an NVIDIA GPU,
Okay, so like if you're NVIDIA specific and you want embedded devices, NVIDIA actually has 1 or 2 devices that are kind of embedded. They're trying to sell them as embedded. They're called Jetson at Jetson Nana, which are small boards, much weaker than like a Titan V GPU or any discrete GPU. But technically, they are positioned as embedded devices. So if you want to use something like this, if you want to use CUDA specifically, I guess you're limited to those kinds of devices because the entire toolchain developed by NVIDIA is proprietary. I cannot really know the internals and the details of like transformation of one binary format into another binary format. There is no easy cross-compilation from CUDA executables into the OpenCL or SpireV executables. But Jetson Nana, just for reference, and other their devices can easily cost like $100. It's generally out of the price range of a classical embedded device. Embedded devices in the industry are normally closer to $10, $20 in terms of their costs. Is the answer better now, or you still have uncovered points?
Thank you.
You're welcome.
So one more question. You mentioned boost compute, but you didn't go into any detail. So why do you not recommend using it directly?
Can you please repeat the question?
You mentioned boost compute,
Yes.
but you go into any details. So I assume you are not using it directly. What are the reasons for that?
Yes, you've got it right. So there is, well, the set of GPU libraries is not infinite, but this table with the boost compute, ArrayFire, and some other libraries was originally much wider. So it had like 20 libraries in it, including VexCL and some other libraries which do more or less the same stuff. I haven't tried every one of them. I've worked with boost compute very, very little, so I don't have enough confidence to talk about very specific details of the implementation. And I generally try to limit my code base in terms of using boost, so I don't have any boost dependencies at all in my code base.
Okay, thanks.
St. Petersburg, if you have a question, come to the microphone in the center of the room, please.
Good evening. I have a questions about implementation this library in FPGA.
Yeah.
You have mentioned about Xilinx.
Yes.
And how to implement the C++ library in VHDL and Verilog world?
It's a very good question. So right now, there's actually a way to compile some of C and some of C++, a subset of C++ into Verilog and into VHDL.
High-level synthesis.
Yeah, but
it's not the same.
Yes. And to be honest, I don't know. I have very limited experience with FPGAs.
Okay. I want to ask about the shared memory and how to solve this problem with Halide or maybe other language and race condition.
Yes, so I guess there will be some kind of abstraction, some kind of a log implementation that will be generated by the compiler that will be injected into every single part of code that may be accessing a shared memory pool. So currently there are basically two research groups, basically the same ones as on the active chart. So as much as I remember, Altera and Xilinx are basically the two dominant companies on FPGAs till now. And Altera is part of Intel as much as I remember. And Intel has its own huge compiler toolchain. So as much as I remember, some of their FPGA generation, code generation goes through their internal compiler toolchain. So I've never tried using it. I've tried doing through the LLVM branch. And I have no direct answer, but my guess is that LLVM generates a log and puts everywhere you use shared memory.
Mm-hmm. And about transition memory model, could some library solve this problem with transition memory model approach?
Can you specify what you mean?
Some approach to solve concurrency.
Transactional, you mean transactional?
Transactional, yes.
Oh, I don't know the answer to this question either. So,
Mutex is simple.
yeah, but FPGA world is very complicated on its own, let alone the architectural principles and like transactional memory. So I would say a more interesting path over here, and at least on a large-scale software development side, is that FPGA software should not really be very well optimized. FPGA software is primarily written for testing purposes. And generally, companies who have resources to do this stuff, they originally plan to transition to ASICs afterwards. So FPGA is like a test bed for them. After the design is complete, they manufacture ASICs for this specific problem. And then after you have the ASIC, the problem is how do you interconnect all the modules and all the accelerators within the device with each other. So this is actually where Vulkan or something like Vulkan may come in. So if we're designing like thread pool environments for the future, we should actually start thinking about them differently. So right now, thread pools, they generally allocate multiple instances of tasks, and they connect them with dependencies so that the next one does not run before the previous one finished running. So what we should start working on is like a more generic approach when some of the operations can be running on devices with very different nature, so that some of them will be running kernels that the host program doesn't know anything about. The same way with FPGAs and ASICs. So I'm not familiar with anyone actually hardcore optimizing FPGA software, but optimizing FPGA and then translating into but like testing and doing something on FPGA and then jumping to ASICs is a more common approach.
Thank you.
You're welcome. Thanks for complicated questions.